And the last part we have is that we have this moving particle that's going through there. Excuse me for 1 second. We have that moving particle that now has left the velocity selector and is moving into the last bit. Okay? So what it is so through the velocity selector, it started off with that voltage accelerator, it's gone through the velocity selector, and now it's traveling through the final stage where it's just simply a magnetic field. Okay, so here comes your particles. Here they are in a magnetic field. Charged particle in a magnetic field, it's positively charged. Okay, remember we're going positively charged moving in this direction. Here's my Q. Put my hand in the direction of QV. I'm going to curl my fingers in the direction of the magnetic field because the field lines are down. I curl my fingers. Oh, see, this is why I use a marker. I do this wrong all the time. QV, curl my fingers into the magnetic field. My thumb is the resulting force, which pushes this object in this direction. Okay? Now, we've talked about force magnetic before. We did it in field forces. But what we didn't talk about is the behavior of a particle that experiences a moving particle that has a perpendicular component to its velocity to a magnetic field line. The behavior, what motion does it have? Well, if you give this particle a little bit of time with that force in that direction, it's going to travel like this. Okay? Do the whole system again. QV, B, force turns into this direction, then this direction. And as it goes through time, it goes over and over into this direction. Okay? It's center pointing. This is a case of centripetal acceleration. When an object enters that, it wants to move in a circular path. As a matter of fact, if there was no plate here, this object would continue to spin around those magnetic field lines. And is the key component of the aurora borealis. Okay? So here it goes. Boom, bang. Okay? So what's happening here is that the charge times the velocity crossed with the magnetic field is producing a force. Okay? And if it's the only force in the system, if we can ignore gravitational, there's no electric field, then we can say that QVB cross B, or QV cross B is equal to MA. Okay? And we can say that the object, even though it's moving at a constant speed, is experiencing acceleration. The velocity, at least the direction of it, is constantly changing. So we can do this. Okay? Substituting in for centripetal acceleration, v squared over r, to my equation. That's the same v. Cool? Now, taking a massive step backwards, we said that the electric field over here at the very beginning in stage 1 is what determines the velocity of that object. We said that the voltage times the charge, okay? And that's voltage, not velocity, so I should put it in a different color. The voltage times the charge is equal to 1/2 mv squared. Now, why am I taking that step back? Well, I'm trying to make my life easier. I'm going to move this 2 over to this side. So we've got 2 times, why I put a cap back on the black, 2 times v, not enough space again. I'll move it over to here. So I'm left with 2, still not enough space. 2 times v q is equal to mv squared. Okay? That can directly go into here. Cool? Taking the mass and moving it over to the other side and taking the square root of it, like we did in step 2, can go into here. Okay, so we end up getting what looks like, and I'm going to erase this section so I have enough room for it, is this. The charge is still there. Now, instead of the velocity term, it's the velocity that we solved for the first part, which is going to be the square root times 2 times q times v over m times e, I'm going to drop the cross product because everything is perpendicular, is equal to this, remember, turned into, jumping the gun, 2q v over r. Okay? Now, what you end up doing with a mass spec is, this could be a photocell, this could be some sort of sensing device. And in the case of a sensing device, that data, that piece of particle hits a bin. And that bin is a particular amount of distance away from that opening. Okay? And where that particle hits, what bin it hits, gives you an idea of the mass value. Okay? Does that make sense? I hope so. Okay? So the first thing I'm going to do is I'm going to remove this Q and this Q. The second thing I want to do is I want to get R by itself. So I'm going to move it over to this side. Okay? So that R goes over to the other side. These two Q's drop off. And I'm left with an R over here. Now, to get it by itself, I need to move all this stuff over to the other side. So B is going to end up on the bottom. And that's going to be times M, dividing by, so the terms flip, 2 Q V. Okay? So this term is now gone. This term is now gone. And I'm left with this relationship. Okay? But I don't like square roots. Not too many people really like square roots. So what I'm going to do is I'm going to square my R, and which ends up turning this into 2 squared, v squared, b squared, and this term drops like that. Cool? Well, one of these v's drops off, and I've got a 4 over a 2. This drops off, and this turns back into a 2. And I'm left with r squared is equal to, and I'm going to rewrite it right here and then erase it right after, 2 over b squared v times what we call the mass to charge ratio, m over q. Okay? That's the end result of the mass spec. Now, we used principles of electric fields in the beginning, moved on to electric and magnetic fields to isolate a velocity in the second part, and in the last part, we're using centripetal acceleration to determine where this particle is going to end up. Which bin, how far away is it from that slot? Okay? Cool? So that is how mass spec is done.